Okay, good morning, everyone. First, let me apologize because I have a technical issue with my camera. I have tried to solve it before the workshop with no success so far. I'm working with my IT college in order to try to fix it. Okay, but unfortunately, I guess that that won't be possible to solve it during the workshop. Anyway, if I'm not wrong, I think that you can hear me well. So, okay, I think that we can go ahead, uh, although you cannot see me. Okay. Okay, so apologize again for that. Good morning, everyone. Thanks for joining today to this SSTAR workshop. I would like to thanks to not all of you, but also to my colleagues from fifth and third for joining, and thank you, Icons, for organizing this workshop within the SSTAR framework. Thanks a lot. As you can see in the agenda, as SSTAR coordinator, I will give you a short presentation with a general overview of the project, okay? And then I will give the floor to my colleagues from fifth and third, where you will be able to see and to hear my colleagues in terms of more technical details about the solid state transformer, the technology and applications, and as well as some environmental evaluation from third, okay, in terms of the high voltage um, with this application of SSTs. Then we will finalize the workshop with an interactive activity that is has been prepared by Icons. Okay, so I guess that it will be really great after the technical explanation of the workshop, and then we will finally go to the wrap up and conclusion of the workshop. So first, let me share my screen so that I can give you a project overview. Uh, Please let me know if you can see my screen.
Yes.
Yeah. Okay. Great.
Not in presentation mode, but you can see.
Yeah. Now you can see the screen.
Yes.
Okay. Great. So again, let me introduce myself. I did it before, but I'm going to do it again. My name is Jonathan Perez. I work in Thursday as project manager, and I am the STAR coordinator. Okay, so the goal is to start today with by giving a project overview of the STAR project. Then my colleagues will give more technical details about this project. Okay. So this is the SSTAR in figures. SSTAR focuses on innovative high voltage solid state transformers. It's a research and innovation action project with a total budget of around 2.5 million of euros, with a total duration of 46 months. In fact, we will finish in February 2026. So the project running from May 2022 to February 2026. The project is coordinated by CIRCE in Spain and involves six partners from four European countries, CERF from Greece, Novamont from Italy, FACEC from Portugal, RINA from Italy, and ICONS from Italy as well. Together, we represent a balance between research centers, industrial companies, and communication and sustainability experts. This slide shows the project structure and the work packages. Work package 2, led by Novamont, develops a bio-based dielectric fluid as a sustainable alternative to conventional mineral oils. Work Package 3 and Work Package 4, both led by FIRCE, focus on the design of the SST module and the development of a decentralized CHP control converter. Work Package 5, led by IFASEC from Portugal, handles prototyping and testing activities. Work Package C, coordinated by RINA, conducts the sustainability and replication assessments. And finally, the last work package of this project, led by ICONS, manage communication, dissemination, and exploitation activities. This setup ensures a comprehensive approach from research and design to validation, sustainability, and market exploitation in order to try to fulfill of the initial objectives of the project. The main goal of SSTAR is to overcome the technical barriers that have limited SSTs to low voltage applications so far. The project aims to increase the operating voltage of SSTs, so that they can be using distribution and transmission networks while maintaining reliability, efficiency, and sustainability. To achieve this, SSTAR works through three independent but complementary research and innovation lines that I will explain in the next slide. These innovations will pave the way toward a new generation of high voltage solid state transformers suitable for commercial use. In fact, the TRL for this project will be a TRL4, but our main objective is try to make a initial research in order to solve those technical barriers until getting to these kind of commercial uses. Okay. These are the main research line of the project. First line is the sustainable bio-based dielectric fluid developed by Novamont from Italy. This new biodegradable fluid enhances insulation, lubrication, thermal performance, trying to achieve up to 50% CO2 reduction compared to traditional oils. The second line is the innovative SST module design led by FIRCE, based on a bidirectional inductive power transfer IPT system using silicon carbon semiconductors. This allows operation at 1.5 kilovolts and 50 kilohertz, with the objective of achieving a total efficiency of 98.5%. And finally, the third research line of the project is the decentralized CHP control converter. Enable the scaling up of modules to reach high voltage transmission levels, ensuring system stability and modularity. And the combined effect of these lines try to significantly improve the maturity and the performance of high voltage space. Sorry. The validation activities will be conducted, are currently being conducted in 35 test beds in Portugal and in Spain, FATEC and FIRCE facilities, to reach to the TRL4 of this project. The FATEC laboratories in Portugal, they are testing efficiency, dielectric strength, and thermal performance. And at FIRCE facilities in Spain, we are taking place in the electronic laboratory in FIRCE by using the hardware in the loop system, the hardware in the loop lab, which allows us to emulate grid conditions and test the control system in realistic scenarios. These two infrastructures ensure a robust and comprehensive validation of both prototypes of the SSTAR project. And as I said, we are currently testing this this testing process in both laboratories, and we will be able to show our results in February 2026 as the project is expected to be finished. As expected, impacts of the project, okay, is expected to generate several impacts from the point of view of technological, environmental, and economic topics. Sorry. Um, Technological impact enable a new generation of digital and intelligent transformers that improve grid stability and renewable integration. Environmental impact through the use of sustainable materials and CO2 emission reductions, and as well economic impact, opening new market opportunities for European industries in the advanced power electronics and transformer sectors. So overall, SSTAR contributes directly to, or try to contribute directly as main goal to Europe's green transition and technological autonomy in next generation power systems. So this is our main goals and expected impacts once the project finishes. We are approaching to these last phases. So our expectation is to fulfill all the initial objectives. We will see, as I previously explained in my previous slide, we are currently testing the prototypes and getting the first results. So yeah, that's all in terms of the project overview. Thanks. I invite you to visit our website and to be updated about not only the initial objectives of the project, but also the different documentation that we will upload, the public deliverables that we will upload, and even our final event that will take place in February 2026. So keep updated about the news and the final results of the project. That's all from my side. Thanks. So my intention was to give a short overview of the project. Thanks a lot. So in this occasion, I know that we will have the chance of having some questions and answers time in the agenda at the end of the workshop. So in this case, I give the floor to my colleagues from first TIRCE and then from third in order to give more technical details about this kind of technology and applications of SSTs. So it's the time to my colleagues Eduardo and Juan. Please go ahead. Thank you.
Thank you, Jonathan. Thank you, Jonathan. This is Eduardo Garcia. I'm a researcher, power electronic in CIRCE, in this research center located in Spain, as well as Jonathan. I am the technical coordinator of this project, STAR, and I am going to present the benefits of the solid-state transform compared to the existing low-frequency transform with my colleague Juan Blanco, who is also a researcher here in CIRCE, who is focusing mainly in magnetic design. So what is a solid-state transformer? So a solid-state transformer are a power electronic converter that provide isolation between a medium voltage and a low voltage system using medium frequency transformer. It means that it's more or less the same as a low frequency transformer, but the operation frequency are higher than the current low frequency transformer that works at the frequency of the grid. So they works at frequencies above of the tens, hundreds of kilohertz. So, and to transfer the energy, they need a power electronic converter to generate the AC voltage in order to transfer the energy between primary and secondary, or secondary to primary. So as one of the main characteristics of these SSTs, of these DC-DC converters is that due to that high frequency of operation, it works at several times per second in comparison with the frequency of the grid. So it means that they need lower volume in order to transfer this energy from one point to the other point. So it's a reduction of size compared to the increment of the frequency. So if we increment the frequency, for example, 1,000 times, it's more or less a reduction in volume of 1,000 times from the same transformer with the same power, but working at the frequency of the grid. So this power electronic equipment needs transistors in order to generate this voltage to transfer the energy from one side to the other side. This is an example of one topology that we have used and we have designed for this STAR project where we are using MPC power topology for transfer this energy. But these transistors nowadays, the market the maximum voltage operation of this transistor only reach 10 kilovolts nowadays in the market, and it's the more common voltages are lower than that, are around 1,000 to 6,000 volts. Okay, so it means that you cannot. There is no transistor in the market in order to go to this medium voltage that we need for this SST application, where we need to interconnect this medium voltage to lower voltages. So what we can use is use this in order to reach this medium voltage. It is possible to serialize these converters in order to reach the demanding voltage of the application. But also it is possible to serialize the converters in order to reach to parallelize, the converters in order to reach the current. So it is like the SST is like a Lego piece that you can serialize or parallelize in order to reach the needed voltage, current, and power of the application, ideally. Okay, so it gives you a big flexibility of operation, but also it is possible to add to one side to add an AC/DC converter in order to interconnect with any grid voltage or frequency, and also it is possible to interconnect and in the other side a DC/AC converter in order to interconnect to another grid voltage and frequency, which allow to the user to control and manage the power and the behavior completely of the equipment. So in this STAR project, we have done this baseline of solid state transformer for this STAR project of a grid interconnected a grid lower than 72 kilovolts. So in this STAR project, we have developed this DC-DC converter of 75 kilowatts with a 72 kilovolts of isolation, and that is one of the main points of the project. It means that the medium frequency transformer that we have used an IPT that my colleague Juan will explain later. It gives us the possibility to give the isolation of 72 kilovolts between one side to the other side. And also in this STAR project, we have developed and we are testing this Cascade 8-bit decentralized controller to manage this Cascade 8-bit to interconnect to the medium voltage line. But for this presentation, we are going to focus on the development of this DC-DC converter of 72 kilovolts of isolation. So I leave the floor to my colleague Juan, who are going to explain more deeply, technically, this development.
Hello, everyone. Thank you, Dardo. So, well, let's say it seems that it's not working.
You can
The
manage?
control, no.
Okay, if not, I can.
So, yes, preferably if you can
Okay.
click.
Okay.
So right now, as Eduardo mentioned, the medium frequency transformer, it's one of the main components in the SST that it's providing that galvanic isolation that was talking about, including on 72 kilovolts isolation and grids of 65 kilovolts and so on. And also this medium frequency transformer, it's reducing size and weight due to that increase in frequency and gives that flexibility that maybe other low frequency transformers do not have. Here in STAR, one of the main contribution is the split planar configuration that we have developed. If you can click again. As you can see here in the little diagram, it's a configuration in which the primary and secondary has no contact between them. This is also called IPT, inductive power transfer, very typical of vehicle wireless charging. So why we choose going into the split planar configuration? We has better insulation since primary and secondary are completely separated. There is increased space between the coils that will be useful afterwards for the thermal design. And also here the usual configuration is a square. I mean, one coil on primary, one coil on secondary. If we can continue. Also, if you can click again. Here the reduce, also one of the main things we want to achieve is the reduced magnetic parameter deviations, in which there is a deterministic coil construction. As you can see in the image, we can, in the design process, make the path for the coils, and this path is usually made by CNC or something like that, that it's really low in tolerances. So this also increases the manufacturability because the coil is perfectly defined and also has great consistency because of that. One of the main improvements also in the STAR project is the double D construction. If you can click again, it's instead of having one square coil, it's having two coils with different opposite directions in primary and secondary. This reduces the stray field losses, minimize the electromagnetic interference, and reduce the losses in the enclosure, the metallic enclosure. This, as can be seen here in the diagram, this is how the flux is going with the double D structure, in which the purple is the magnetizing flux, which is the link between primary and secondary, and the green areas are the leakage areas. As you can see, the leakage areas are mainly referring almost in the middle and some part of it on the sides, but the main part it's in the middle. You can click again. This is the results on the simulations and the comparison between the rectangular and double D coil. As you can see, the main part is that the enclosure losses, which what we want to minimize, goes from 270 to 4 watts. So it's almost none, with a little bit more of core losses on the double D and DC losses, DC AC. But in general, there is a loss reduction. You can see here in the simulations how the square has more losses in the enclosure. You can follow the next one. Now with the thermal behavior, as you can see again, Eduardo, there is enough space for oil to flow in both cases, for the double D or the square one. This is a thermal simulation. The left one is the square one, and the right one is the double D. You can see that in the double D, the maximum temperature is less, and also it's more confined into one area that is in the middle of the coils. the enclosure is not heated, so that's why the oil it's more it's less heated, has less temperature than in the rectangular coil. Right now we are with the prototype construction. There is no oil in our prototype. In the prototype that is designing one of our partners, FASEC, it's with the oil. Right now we are testing the limits of the power electronics, and as you can see here in the left, it's the design we have in 3D for the prototype, and then on the right, how at the end how it's constructed. You can see that it's almost the same between the design and the construction. So we have very deterministic way from the design to the construction path. Right now, if you can continue. Right now we are with the testing. Right now we make the small signal measurements done with the equipment about 100. And we are expecting right now to gather more information for the large signal characterization when we start to move more power with the system. Here you can see some of the plots of the boat 10, boat 100, and then all the elements of the model, the capacitors and the magnetizing and leakage inductance that we have obtained with that small signal measurements. And with that, we can continue with Eduardo.
Thank you.
That we will
Thank you, Juan.
finish.
Okay, thank you, Juan. So, as we have seen, it means that we will be changed this with SST. We will change all the low frequency transformer. Well, we think that it is not. We are not going to change, but because the low frequency transformer, it's from my point of view, is one of the best machines done by human, because it has a very good efficiency, very good reliability, and also it's a very mature technology which increase the reliability, of course, but also reduce the price, because it has been developed since 100 years. So it is a very good equipment machine, but the SST has its benefits, and one is, as we have said before, you can reduce a lot the size and the weight of the transformer, and it has the market in the transportation, mainly for example, for trains, for vehicles, and also for planes, due to the low weight of the converter. Furthermore, if we need a DC-DC converter in order to interconnect to the medium voltage DC lines, it's the only way to do that. We need an SST for doing that, for going to low voltage DC to medium voltage DC. There is no another way. So in a grid that are moving from AC to DC, due to that, a lot of our generation percentage and a lot of our loads are in DC. So if we interconnect all of them in DC, and we interconnect all of them in medium voltage DC, we are going to need these SSTs in order to interconnect them and to avoid the use of the reduction of different stages of conversion if we are only going from generation to loads in DC instead of going to AC. But also, it's one of the main also benefits is the controllability. For example, if we perform an SST for the AC grid, if you want to interconnect the AC grid to a medium voltage DC line, an example like this, or can be, for example, a data center it's a very demanding infrastructure nowadays. This SST allow you to the complete control of the power, bidirectional power, and also to the management of reactive power It also allows you to regulate the voltage and the frequency depending the power of the SST, but you can control it in order to stabilize the grid, and also you can protect very instantaneously protected the primary from the primary to the secondary, and also to perform black start if some problem has been if the grid has some problems. You can do it both in AC and in DC. As an example of SST, during this year we have performed in Taigon project, we have performed the commissioning of an SST in Taigon project with a higher TRL than STAR project. So we have done an SST that where we reach the 3 kilovolt the DC voltage with an SST of 150 kilowatts with a peak power of 200 kilowatts bidirectional, fully controllable, and we have tested in the project at nominal power. So thank you. That's all from our side. I leave the floor now to my colleagues from CERT.
Hello, everyone. Hi. Can you hear me?
Yeah, we can hear
Yes,
you, Maria.
Maria.
I'm trying to share my screen, but there is no option here.
Maria, I'm trying to allowing your option. Let me check. Otherwise, we can share for you. Okay. You should be able now to share your screen.
Yes, perfect.
Okay.
Thank you.
Great.
Okay. Please tell me if you can see my screen now.
Yes, we can hear.
Maria.
Okay, and then presentation mode, I suppose.
At the bottom
What happened here?
right. At the bottom right. Yeah.
This one. Okay, good. Okay, so hello everyone. This is Maria Fotopoulou from CERT, and I'm here to present a less technical and more theoretical presentation, also related to the STAR project. And this one is about the integration of direct current renewable generation into the medium and high voltage grid. So, the conventional power system, as it used to be in the past century, it was quite passive, it was unidirectional, and it was also based pretty much only on thermal generation, like coal. It was just as simple as you see it in figure 1, and it was stable, simple, and reliable, but it was not environmental friendly, and the resources that it utilized were limited, such as coal. So there was a need to seek different resources. These are a few words about the background, as you see. And when we say different resources, the main emerging solutions are the renewable energy sources and the energy storage systems. When we say renewable energy sources, we mostly mean photovoltaics and wind farms. And when we say energy storage, we usually mean lithium-ion batteries or any other kind of battery, fuel cells, hydropump storage, and so on. Now, the thing is that many of the aforementioned resources, they are quite different when it comes to their integration to the power system. For example, they're quite small and distributed. They're not like the large centralized production that we used to have. Moreover, their production is not predetermined, it is stochastic, especially when it comes to photovoltaics and wind farms. and they usually operate in medium voltage or low voltage. They can also be connected in high voltage. And the main thing is that their production is usually DC instead of AC. For example, the photovoltaic produces DC, the battery energy storage systems give DC too instead of AC. Therefore, the infrastructures and the equipment need to be upgraded in order to guarantee the power quality and stability with these new resources. And the solution in this case is to get DC links between, wherever applicable, wherever convenient, between the DC sources, the DC storages, and the DC loads, which can be data centers, electric vehicles, electrolyzers, and so on, in order to have increased efficiency and avoid the extra and unnecessary AC stages between these DC resources. Then the other thing is that we need to have advanced systems to facilitate AC-DC connection and to have highly controllable devices. And therefore, here the key, the core technology for enabling all of the above is a solid-state transformer, which is the purpose, the main subject of the STAR project. So this is the main concept of a solid-state transformer. This is a figure from our joint publication with a couple of years ago. It shows that the solid-state transformer does not only facilitate the connection between medium voltage AC and low voltage AC, but it also has medium voltage and low voltage DC links where one could connect DC loads such as electric vehicles and DC sources such as photovoltaics. Therefore, unlike the conventional transformer, the SST can facilitate the connection of both AC and DC in both low voltage and medium voltage levels. So the SST is more advanced and controllable than the conventional transformer. And of course, if you combine such modules, you can reach even higher voltage levels. Now I have two examples of future prospects for SSTs in DC renewable generation and its integration into the power system. Here we have a photovoltaic park. This is the classical approach for power delivery at utility scale solar PV plants. It is the one we see on top. The photovoltaic produces DC, then it is turned into low voltage AC, then it is medium voltage AC and high voltage AC. But if one uses an SST, then we get the two configurations on the bottom of this slide. In the first one, we have multiple SSTs that convert the PV production into medium voltage AC directly. And then we have a more advanced option on the other side that says that we have multiple SSTs that convert the PV production directly into medium voltage DC for the integration to the power system. And then we have another quite popular application. We have the offshore wind farm. On the left side, we see the classical approach for power delivery at utility scale offshore wind farms. The wind farm produces AC, which is always converted to DC and then AC again. And the conventional classical approach would be to have low voltage AC, medium voltage AC, and then connect it into high voltage DC. But if one adopts the SST solution. This is the alternative SST configuration on the other side of the slide. We have multiple SSTs, so the wind farm production is converted directly into medium voltage DC and then again to high voltage DC. So these were the two main applications. And here I have a table from our joint publication with IRTE with some of the main interesting SST prototypes for this purpose. We see that there's plenty of them, which proves the market value of the SST. These are developed by researchers, by institutes, by the R&Ds of production companies, many industrial partners, and so on. And then at the bottom of the list, we also see the newest prototype, which is the STAR project. And above that, we see the Tigon project, where another SST was developed. And here we can see that the application is mostly in DC renewables, but it can also be in railways, EV charging stations, marine applications, smart buildings, and data centers. And here we have a map that proves the worldwide interest in solid-state transformers of this scale. These are the identified stakeholders that have published SST prototypes with relevant features to the STAR project. It is not a scaled-down prototype, and it has rated power. They all have rated power higher than 25 kVA. So, getting to the point in more detail to the project, the question would be, how does the STAR project contribute to disintegration into medium voltage grids? And here we have a MATLAB simulation that we performed in SERTH. It is a combination of solid-state transformers, 4 of them in series in MATLAB. On one side, we have the connection to the power system, and on the other side, we have batteries connected to each of the solid-state transformers. So we have 4 batteries. And this is a zoom in of the dual active bridge with the high frequency transformer, 1 per SST. And these are some of our preliminary results. These are all simulations, but still, this is the charging mode where we can see the H-bridge AC voltage, we see the capacitor DC voltage, we see the voltage reference and the voltage angle, and this is the zoom in. And then we have the same or the equivalent on the discharging mode. And this does not only prove that the concept of disintegration into medium voltage grid is feasible, but also that the STAR project makes it even smoother, and this is the zoomed in version. So this is pretty much all from my side. Do you have any questions, or I leave the floor to Marikatia?
Yeah, Maria, the questions will be done at the end of the workshop. Okay, so yeah.
Okay,
we can
good.
Continue.
Good,
Yeah,
perfect.
thank you, Maria. We can continue with your colleagues. Maria.
Okay, hello.
Hello.
I'm Marikatia from SERTH. Let me share my screen. Okay. Okay, hello everyone. Thank you for being here today. I'm Marikatia from SERTH. I'm presenting you the life cycle evaluation of this innovative SST. As you already get informed, the energy transition towards a decarbonized economy is changing profoundly the infrastructure of power grids worldwide. SST have emerged in the last years as a technology able to extend the typical functionalities of a regular transformer, optimizing the power flows and introducing a high degree of digitalization in the network. In this presentation today, the life cycle assessment methodology implemented to quantitatively evaluate the environmental impacts and benefits of this proposed SST throughout their life cycle, encompassing various stages, including production, operation, and decommissioning of the project. The functional unit is used 1 kilowatt-hour of transferred electricity, reflecting the emission normalized by the total electricity throughout over the transformer lifetime. The system boundaries is from cradle to grave. It includes energy and mass balances of all the referred stages production. That includes the raw material extraction till the module production, the transportation of the materials to Spain, and the operation and maintenance, as well as the disposal that includes the recycle and landfill disposal. 3 scenarios investigated. First one, the baseline scenario that includes the assessment of the environmental impacts of the current states of the grid of conventional and high voltage transformers. The second scenario is the take into account the evaluation of STAR module, and the scale-up scenario that could involve deploying the high voltage SST transformers in a large radio grid or network, handling a higher capacity of electricity. In our case, we just use main STAR modules. First of all, here as a baseline scenario, data from the literature was used to calculate the environmental impact of the conventional transformers. Data was adjusted to align with the functional unit of the project in order to be compatible with the STAR module. The figures here depicted the global warming potential in terms of grams of CO2 equivalent per kilowatt hour for transformer, with varying nominal capacity. Both figures highlight the relationship between transformer capacity and the environmental impacts. The first figure, as we can see there, you can see here, illustrated the transformers with capacity higher than 10,000, and the other one with capacity lower than 1,000. And this revealed that transformers with lower nominal capacity generally exhibit the higher global warming potential values per kilowatt hour of electricity transfer. This shows us a greater environmental burden. Conversely, as the nominal capacity increases, the global warming potential decreased, demonstrating improved efficiency and reduced environmental impact. It's worth mentioning here that our high voltage SST main components are the IPT tank and the PCB that consist of individual parts. A tank, for example, and electrical isolation bushing, windings that are main components of IPT tank, and composed of different materials. Steel and electric fluid cover more than 74% of SST. One of the innovation keys of STAR module is the eco-friendly bio-based electric fluid. That it was evaluated the production of 1 kilo of this using different impact assessment methods. The global warming potential, as you can see here, ranges from 1.26 to 1.35, while the cumulative energy demand from 15 to 17 megajoule. This has minimal variation between the methods, and this consistency suggests that the environmental performance of the electric fluid remains robust regardless the assessment approach, providing confidence in its low environmental impacts across different evaluation frameworks. A comparison of STAR fluid with mineral oils from literature, that is an alternative option of transforming fluids, so that STAR fluid outperforms the mineral oils in terms of global warming potential, with percentage differences ranging from 33 to 69. Furthermore, STAR bio-based electric fluid exhibit competitive performance compared to other vegetable oils into literature, and also environmental impacts fall within the same order of magnitude. However, certain variation in results are due to differences in database or methodological approaches that each study follows, or else the delimitation of system boundaries and adopted. The total electricity transferred by one module over the 35-year lifetime is calculated, assuming a constant 100% average load and transformer capacity of 75 kilovolt ampere. Taking into account these parameters, we can see the contribution of its phase to the total environmental impact. As you can see here in the first graph, The operational phase is the dominant contributor, responsible for 96.6% of the total impact, highlighting the importance of operational efficiency, while production contributes to less than 4%, and the transportation has negligible contributions. Lastly, the negative disposal value, contributing to the reduction of the overall system footprint, arise from the recycle of the materials, such as steel, which can reflect the avoided emissions linked with the extraction and the refining of new steel. And in the second figure, we can see that similar outcomes derived regarding the resource use. It's also want to highlight that the operational phase was modeled using the 2023 European electricity mix to account for the operational losses. A sensitivity analysis of STAR modules regarding the operational phase, focusing on the impact of different energy sources used to compensate the energy losses. Two different impact assessment methods used. Since the transformer is designed for use in RES, the analysis evaluates how varying the energy mix comparing the European energy mix 2023, the fossil-based energy mix, electricity mix, and RES-based grid mix, and how this all affects the environmental impact. The focus is primarily on global warming potential, and this highlights the influence of the energy source on the overall sustainability of the system. The operational lifetime of the transformer is also a critical factor influencing its overall environmental impact. In this sensitivity analysis, the lifetime varied from 30 to 40 years to assess how extending or shortening the transformer service period affects the environmental footprint, and basically in terms of global warming potential. So it is obvious that the longer the operational years, the lower the environmental impact. In addition to evaluating environmental energy integration, a sensitivity analysis were performed on average load of the transformers to account for varying operational conditions. While in the base scenario assumes 100% average load, this analysis explored the environmental impact over more diverse load levels. As you can see, as you can observe, the higher the load, the lower the environmental impact per kilowatt-hour of transferred electricity. This approach provides us understanding of the transformer performance across different operating conditions. An important performance indicator, the delivered energy efficiency, which quantifies the energy output of the transformer technology in relation with the total energy input required throughout its expected lifetime, show that 0.96, and this gives us the result that mainly the efficiency is dominated by operational losses. Finally, another performance indicator was estimated, the CO2 payback time, which identifies the required year of the SST to offset the carbon dioxide emission produced during its production. The result of CO2 payback time is 6 years, is quite high. However, we should take into consideration the relative this difference can be attributed to a high conventional transformer nominal capacity, the life cycle impact assessment method that each study have used, and the different system binders that each system have adopted. That's all from my side. Have you any questions? Thank you for being here today.
Thank you, Maria. Thank you. So, Erika, I think that it's time for going ahead with the interactive activity that you have prepared.
Yes, thank you, Jonathan. Hi, everybody. Good morning. We now move to Mentimeter for quick interactive activities to collect your input and that are helpful for us as STAR to understand how to move forward and understand the possible challenges, barriers, or positive aspects for the future of solid-state transformers. We move to Mentimeter. You can scan this QR code or go to Mentimeter. I just put in the Q&A section here the instructions and the link to click on. So we leave you some seconds to go to Mentimeter. In the meantime, if you have any questions, you can either raise your hand and we can listen to your question, or you can type your question on the in the Q&A section here on Teams, and we collect all your questions. So we are ready. Let's wait probably another couple of minutes. Our suggestion is to go to use the QR code to use the Mentimeter on your phone. Otherwise, you can click on the link that you find in the Q&A section so that you use it on your laptop. I think we are ready to start. So we go ahead with the first question. So in one word, what comes to your mind when you think of the future of power systems with the solid-state transformers? This is a word cloud, so just type what comes to your mind by talking about solid-state transformers. We leave you a couple of minutes. Think also about the possible applications that we can have for solid-state transformers. We are collecting some inputs, smart grids, electric vehicles, I guess, DC transformers, energy efficiency, better control. It's interesting. Okay. I don't know if Jonathan or the other speakers have any comment on what they see from a technical point of view. This is, of course, just an icebreaker. Then we move to more intensive questions, but just to open up the discussion.
Yeah, maybe my colleagues or either from fifth or third, because it seems that one of the most repetitive word is flexibility. That, if I'm not wrong, is fully aligned with the objectives of the project. So I don't know if someone from my colleagues need to add something. And So I think that it's one of the main objective of not only for SSTAR but also for the SSTs in order to increase the flexibility of the power grids. Yeah, Eduardo?
Great.
Yeah, you're right. I mean, okay. Also, I mean, it's the controllability of this kind of equipment is one of the main objectives of why you are going to invest on this technology, because you need flexibility to interconnect all that you need depending your necessity.
Great. Okay, thank you. This was just an icebreaker. We can move to the next question then. Here, which of the following factors must hinder the adoption of solid-state transformers today? This is because we are interested in collecting what are the main barriers to the adoption of solid-state transformers. Here you need to rank the options, so from the most important to the least important that you think. Okay, some votes for cost and manufacturing scalability, low awareness or confidence in technology. We'll give you another 30 seconds to rank your answers.
Yeah, but currently we achieve the scalability.
We can already guess.
Confidence. Yeah, so low confidence on the technology. That's the reason of the importance of this kind of research projects.
Yeah.
In order to try to find how to scale up this kind of technologies and try to get effective results in order to get a higher confidence in the technology and finally to try to go to the market. Eduardo, or
the AC equipment nowadays are very mature technology, so it's very difficult to compete with them in cost and also in reliability, because it's the TRL of these products are low nowadays. So and the AC equipment are very good, proven and mature. So it's very difficult. But I think there is a gap in case of the cost. There is a gap integrating generation and loads in DC at medium voltage. There is a gap there, and I think we are seeing a lot of movement regarding that in order to increase at least the integration of photovoltaic, of trains, of data centers in medium voltage DC. And it's where this SST technology are going to be increase their reliability and reduce the cost. It's where is the place where this technology are going to be introduced in the market. And also the lack of standards. We are working a lot in DC, and it's one of the main topics regarding the DC integration, because it's not very clear how you integrate in DC different generation and loads. It's not it's not so study and the information. It's not so big and enough in case of standards regarding this integration instead of AC integration.
Thank you for the comments. And it's helpful for us to understand also the external point of view about the barriers for solid state transformers adoption. Okay, we can move to the next question, I think. So in which applications do you see the highest potential for solid state transformers in the next 5-10 years? So for example, electric vehicles charging, renewable integration, ports, buildings. So that's more practical questions to go into the real world adoption of solid state transformers. So yeah, here is an open question. So feel free to write. Oh, interesting. We have 2 data centers. And electric vehicles, microgrids. That's interesting. Harbor. Yeah. Data center is a very common application. I don't know if you, Eduardo, comment how.
Yeah, the data centers are now, I mean, there are a lot of market there nowadays. There are a lot of movement. So the load of the computers works in DC. So you need to integrate this load into the AC grid and very high power demanding. So it is where SST can outperform maybe the low frequency transformer, depending the integration and how you do all the topology. I mean, and they're out of now. For example, I know that NVIDIA it's moving to 800 volts DC, and for sure they will be incrementing the voltage in the future in order to reduce the losses and increase the efficiency. And in marine application, in harbor application, I think also it's very I like that also because the electric ships needs a lot of power, and there is a problem regarding where you are going to charge these electric ships, because the ships are moving around the world, and we have 2 different electric grids, one working at 760 Hertz, the American one, and the European on more countries at 50 Hertz. So if you want to have this intercompatibility, you need to integrate in DC like EV chargers, but with high power, because we are talking about ships, we are talking about megawatts, and it's where SSTs are going to go. I mean, to increase the market. I mean, in these cases.
Yeah,
I'm agree with that, and also EV charging for sure EV charging.
Yeah, and do you want also to comment something about the electric vehicles with very common use? We can also the general public can see the impact of solid state transformers.
I mean, it's the same, but in case of the electric, in case of the electric cars, the voltage are going to be lower, not so much as this medium voltage that can be the ships, for example. But yeah, it's also, we are talking about integrate a lot of power in DC to the electric grid. So these SSTs are going to, I mean, also integrating these EV chargers to the AC grid, but also integrating these EV chargers with storage and DC generation like solar panel. All of them in medium voltage DC line it's a very good can give you a very good performance for this kind of application.
Okay. Great. Thank you, Eduardo, for commenting on these answers. Okay, I don't see any other answer coming, so we can go to the next question. So how confident are you that solid-state transformers will be widely adopted in Europe by 2035? So this is to test your confidence, as we have seen in the first question. It's in the second question. Sorry, it's a very important aspect, confidence in the technology adoption. So this is to test your confidence. Okay. First, the podium is for moderately confident, so midway, nobody fully confident. One answer, not at all. It would be interesting to understand why not at all. If the person who voted wants to intervene and explain, otherwise we can.
Yeah, but it's good to see these results, Erika, because yeah, Jessica is raising hand, but one of the most repeated, not the most one, but one of the most worst that is repeated in our contractual documents in this project is challenge. Okay, so this is a challenge. Yeah. This is a challenging project. So yeah, so it's normal to see this kind of results of me that even not at all confident. Jessica, I think that she's raising her hand.
Yeah, hi, can you hear me?
Yes.
Hello. Yeah, I was the one who voted not at all confident because I mean, you're with this research project is has a goal of reaching TRL4, and then the grid takes a really long time to adopt anything, and we already mentioned that there is like lack of regulatory support. So having wide adoption of that technology that hasn't even reached high TRL levels in the next 10 years, I don't see it happening. I do see the value, of course. It needs to keep being developed, and I think there needs to be more pilots and projects in the applications that Eduardo was highlighting, like harbors and data centers, so that the value can be proven, and also the reliability that Eduardo also highlighted, that I mean the incumbent transformers do have, that these new technologies do not really have that certainty, and reliability and resiliency of grids is of incredibly high importance. So yeah, I don't see it happening in the next 10 years.
Thank you.
Hi, can I answer that?
Yeah.
Can I answer that? Indeed, the STAR project has a low TRL, but we have seen SSTs in other projects with higher TRL. For example, in the Tigon project, we had the TRL of what? 7 or something. Yes, 7. So this means that there are, steps towards this direction. It is starting to get implemented by the market gradually.
So do you see any chance in 10 years, Maria? Or Eduardo, I don't know who wants to answer. Or probably what? More. Do you see any chance for the adoption of solid-state transformers in 10 years, or do you think we will need?
Sure, yes, sure, okay. But not everywhere. Like in very specific applications, you cannot replace everything.
Okay, thank you. Thank you for clarifying. Okay, nice discussion. We can move to the next question, I think. If anybody else want to add something. We go to the next question. So which type of collaboration would make the biggest difference, which is linked to what we were saying, for solid state transformers adoption? So here you have to kind of rank and give an evaluation in numbers for each of these aspects. For example, from 1 to 5 for research and industry partnerships, from 1 to 5 for cross-sector pilot projects, and so on. Okay, let's see. It seems that research and industry partnership is the most rated. Okay, yeah, which is really linked to what we were saying also for the previous question. It seems that research and industry partnerships is the most rated. Then we have standardization initiatives and EU policy frameworks, as we also mentioned earlier. It is indeed a gap we need to consider. And then we have cross-sector pilot projects. We mentioned other projects also that are dealing with the SSTs and public awareness campaigns. It's for this kind of specific and technical topics. I agree that it's the least important as a collaboration, at least for the short term. I mean, we first need to have collaborations and the industry partnerships, for example, and consider the EU policy gaps, and then we can consider the general public, I mean, which comes later. I don't know if anybody else have questions or comments on this. This was the last question, so that was to collect your input and open up a discussion. Do you have any other questions from the public, or otherwise, if you don't have any other questions for the speakers on the project on solid state transformers, otherwise I think we can move on to the conclusion. I think I don't see any hands raised. Thank you for the nice discussion. Jonathan, I don't know if you want to close the meeting.
Yeah, briefly, first, obviously, thanks to you all for your participation, not only from my colleagues from the SSTAR project, but also for the rest of attendees here that joined with us today. It's been a fruitful workshop today. We have shown the work that we have been carried out during the last years in the SSTAR project. We are approaching to the end, so we will be able to show more results in a few months ahead. Thanks for the work that you have been done so far. We have to keep working until the end of the project. Thanks to all for your participation and your interest in this topic as well. As we have seen, this is an interesting topic to be discussed and to keep working with. because there will be a lot of challenges, technical challenges, in order to go ahead until the market applications. Obviously, it's crucial to perform this kind of research projects in order to understand better this kind of technology, in order to test which kind of solutions must be implemented to solve these technical barriers that we initially identified. And yeah, then we will see the more research we will perform, the sooner we have this kind of standardization that we are discussing in the during the Mentimeter. Okay, so we are aligned with this kind of responses, research and standardization. Okay, but both of them are linked in order to progress with these technologies. So yeah, we keep on this. We will keep on this working, researching, and we will see the future and this kind of application. Thanks a lot again, and yeah, I invite all of you to keep updated of the SSTAR project. Visit our website and our next public events, especially not only for this kind of workshops, but also we will make some public posts about our upcoming organization of the final event in February 2026. Okay, we are working on this and to define some topics. And yeah, thanks to you all. Have a nice day, and thank you. Anything else from my side?
Thank you. Thank you, everybody, for joining.
Okay,
Thanks a lot.
bye
Have a nice
everyone.
day.
Bye. Thank you.
Bye.